So at this point we're ready to begin talking about something called a derivative. The derivative is an incredibly fundamental piece of what calculus is. It's incredibly important, and it's just a big thing. But I think in order to really understand it, we need to spend this video just talking about what this thing is, right? So we're going to be talking about the derivative of a function. And what's hard is that the derivative is a function in and of itself. So it's like you started with a function, and the derivative of that is another function that's related to that one. So it's sort of like every function comes with a backup derivative function built into it, right? So this is going to make sense through the course of the video, but it's a little bit cerebral, so make sure you've got your brains turned on. To get away with this, we're going to have to recall what a function is. A function is just something that takes an input value and gives back at most one output value. That's all there is to it. All it is that there's an input and it gives you an output value. Like that's all there is to a function. Okay? Now, in this part of the video, I want to talk about what the inputs and outputs mean in both the original function and the backup helper derivative function thing. Right? So the first question is a recall question. In fact, these are both kind of recall questions now that I think about it. What does it mean when we say that g of 5 equals -4? And you could think about that either in terms of input and output or in terms of the graph. So pause the video for like 10 seconds and remind yourself, what does it mean when we say g of 5 equals -4? What you should be saying, and the thing I'm mostly looking for, is that the graph, that g of x, has a point at 5, -4. What this statement says, what it reminds us of, is that when we evaluate a function at a value, it gets us the y-coordinate at that point. When we plug a number into g, into the original function g, and get a number back, that number is the y-coordinate of the point. Okay? Now the newish thing, new to you yesterday, what does it mean when we say that g prime of 5 equals 2? Like, what does that thing mean? Right? And I hope you'll pause and remember from yesterday. That means, because there's the prime, this is a statement about the slope of the tangent line. This means that g of x has a tangent at x equals 5 with slope 2. And that in some sense, that's all there is to say right here. Right? When you have a number being plugged into the original function, it's getting you the y-coordinate of the point. When you have an x-coordinate being plugged into the derivative, that number is the slope of the tangent at that x value. That's what the output of the derivative function means. And so in the previous, the title for these notes is the derivative of a function as a function. What I'm telling you right now is that we could think about this g prime function as being a function. You input the x-coordinate, and what it outputs is not a y-coordinate. It outputs the slope of the tangent line. That's what this derivative function is going to mean. The more I look at this question, the more I love it. This is the first time I've ever asked this question before, and I'm really excited about it. And I want to try and not help you. I want to try and have you do it on your own. One of the challenges in this class is that a lot of times I'm going to be asking you to do things you haven't done before. And you're going to have to read a problem and understand what it's giving you, and understand what it's asking for, and put together things you've done in your past. This question, you know how to do. I've given you all the tools you need in yesterday's videos and in the intro today. So I'd actually like you to pause the video and try this on your own. This example says, consider a function h of x with h of 2 equals -1 and h prime of 2 equals 6. Write the equation of the line tangent to h of x at x equals 2 in point-slope form. So pause the video, see if you can understand what I'm giving you, and see if you can give me what I'm looking for. Okay? In my mind, doing problems like this means, look at what they're asking you to do. In fact, a lot of times I'll say find the verb. The verb in this problem is write. That's what they want you to do. I mean, consider is also a verb, but what they really want you to do is write something. Write what? Write the equation. What equation? Write the equation of the tangent line, right, in this form, right? And so sometimes we'll start by saying, oh, point slope form, I know that. It's y minus y1 equals m times x minus x1. There it is. And now we start thinking, if only I had a point and a slope. So you start looking back at the rest of the problem. And then you recall, hey, wait a minute, doesn't this mean that there's a point at 2 comma negative 1? And then we start thinking, hey, doesn't this mean that the slope at x equals 2 is 6? That's exactly what it means. And so you have that information, we just plug it in. Y minus negative 1, so y plus 1, equals the slope 6 times x minus 2. Yay, we're done. I mean, very, very easy question. If you have already the statement of the point and the statement of the value of the derivative, we can very quickly write the equation of the tangent line. So now I'm going to step this up one level of difficulty. In this example, I'm giving you the function. I'm saying given that f of x equals x squared minus 5x plus 4, I'm also giving you the derivative. And given that f prime of x equals 2x minus 5, find the equation of the line tangent to the function at x equals negative 1. Now, I want you to remember, what are the outputs of these two functions? What do the outputs actually mean? When you plug a number into this original function, what does the output represent? The output represents the y-coordinate of the point. When you plug a number into this function, what does the output of that function actually represent? The output of the derivative function represents the slope of the tangent line, right? So if I want to find the equation of the line tangent to this function at this point, I'm basically going to need to find a point, and I'm going to need to find a slope. How will I find the point? I'll find that by evaluating the original function, because we know that's the point. That's the point. Sorry. The purpose of the original function is that it gives us back a y-coordinate. So if I do f of negative 1, f of negative 1 will be negative 1 squared minus 5 times negative 1 plus 4. Sorry, those were some sort of ugly numbers in there. F of negative 1 will be 1 plus 5 plus 4. So it looks like f of negative 1 is 10. Great, so the point is negative 1 comma 10. What about the slope? How do I find slope? Well, fortunately we have a derivative function. And the purpose of that thing, the output of that function, is that it gives us a slope. So if I just do f prime of negative 1, that'll give me the slope. F prime of negative 1 is 2 times negative 1 minus 5. Looks like f prime of negative 1 is 7. So that means my slope of the tangent at x equals negative 1, that slope is 7. By the way, I'm almost always going to reference the slope of the tangent at a value, because this function has tons of tangents, and the one I want is this one. Okay. So if I wanted to write the equation of this tangent line, I just use point slope form. Y minus 10 equals 7 times x minus negative 1, so x plus 1. So that's how we do this. Okay. One more example. I want you guys to consider the function g of x with g prime of x equal to x squared plus 3x plus 1. I want us to find the equation of the line tangent to g at the point negative 2 comma 7. So this should be similar to the previous problem. Pause the video and figure it out. So the idea here is this is a little bit different. In this case, they actually gave us the point already. All we really need is the slope. Right? How do I find the slope? Well, I have a function right here. That function gives outputs of slopes. We just have to plug something appropriate into it. Right? I guess I could see people being confused, like, well, what should I plug into it? Should I plug in negative 2 or 7? And I would say you should answer that yourself. Look at this function. What do you think you need to plug into it? It says g prime of x. So you should be plugging in the x coordinate of the point that you're working with. Fortunately, you have a point. Its x coordinate is negative 2. So hopefully you've already done this on your own. If you haven't, pause the video. You should be doing this problem on your own. We've got g prime of negative 2 is negative 2 squared plus 3 times negative 2 plus 1. So g prime of negative 2 is 4 minus 6 plus 1. That means g prime of negative 2 is negative 1, and this thing is the slope that I was looking for. Now I have a slope and I have a point, so because we love point-slope form now, we can very quickly write the equation. Y minus 7 equals negative 2, negative 1 was the slope, right? Negative 1 times x minus negative 2, so plus 2. And there we go. So in this video we sort of covered, like, if you have a derivative function, if you have this thing, we can use it to find the slope, and we can use that to find the tangent line. I hope, though, that there's a question that's sort of like burrowing into your brain. And that question is, where did this thing come from? Like in several of our problems I just kind of mentioned, oh, and by the way, this magical derivative function that gives you every tangent slope you could ever want. That derivative function, here it is. I have not shown you how to find that derivative function. And the good news is that that's coming up in the next video. So if you're interested in that, it's coming. If you're not interested, you need to watch the video anyway, because we need into other stuff. So I'll see you in the next one.